This chart plots the trajectory of global data center electricity consumption. From a baseline of 415 terawatt-hours, an aggressive 12% compound annual growth rate drives the projection until it crosses the 1,050 terawatt-hour mark by 2026. The primary constraint on training the next generation of frontier AI models is no longer algorithmic design. Writing better software will not solve the bottleneck. The challenge is entirely physical. At the macro scale, operators must secure gigawatt-scale electrical grid interconnections just to power the facilities. At the micro scale, they have to engineer sub-microsecond networking protocols capable of linking hundreds of thousands of individual GPUs. Hyperscalers cannot simply buy more silicon to keep models growing. They must simultaneously solve the macro physics of energy delivery and the microphysics of data transmission. A standard cloud data center allocates a fraction of its total power to compute. In a facility optimized for AI, 75% of the total electricity flows directly to the servers. This concentration is driven by the AI accelerators themselves, which draw 2 to 4 times the wattage of conventional CPUs. This topology map contrasts a traditional electrical grid with an AI facility. Legacy grids supplied distributed consumers, not continuous gigawatts to a singular point load. The AI load instantly erodes safety margins, pushing substations and transmission lines to their thermal limits. In mature data center hubs like Dublin, data facilities can consume nearly 80% of local demand, triggering severe power shortage warnings from grid operators. Expanding that capacity requires building new high-voltage transmission lines and substations, a process trapped in a 7 to 10-year interconnection chain. To circumvent these queues, technology companies are acquiring dedicated carbon-free baseload generation directly. Purchasing entire nuclear power plants allows them to secure gigawatt-scale power without waiting a decade for grid upgrades. On the software side, operators mitigate grid strain through dynamic load shifting. During periods of local grid stress, facilities automatically throttle or pause less time-sensitive background training jobs, instantly dropping the data center's total power draw. Simultaneously, active inference queries are redirected geographically, routed away from strained grids to data centers with spare renewable capacity. Power constraints have forced AI hyperscalers to operate as global energy balancers, dynamically managing multi-gigawatt loads across continents in real time. Inside the facility, the power grid gives way to an internal physical bottleneck, thousands of GPUs attempting to share massive datasets continuously. At this scale, network latency carries a strict mathematical cost. If data delivery stutters for even a fraction of a millisecond, thousands of highly expensive GPUs sit completely idle. This schematic details traditional high-performance networks, highlighting the remote direct memory access pathway. These protocols achieve ultra-low latencies via kernel bypass. The data packet speeds through the network, skipping the operating system entirely to write directly into remote GPU memory. But InfiniBand carries a rigid constraint. It mathematically requires strictly ordered packet delivery. Every piece of data must arrive in the exact sequence it was sent. To prevent dropped packets and maintain this order, traditional networks rely on priority flow control, a mechanism that pauses traffic when congestion occurs. At Hyperscale, priority flow control encounters a fatal failure mode known as head-of-line blocking. If a single dropped link or congested path pauses one stream, a rapid chain reaction freezes all surrounding data streams instantly. This localized pause cascades outward, triggering a massive deadlock across the entire GPU cluster and halting the training run. The traditional rule of high-performance computing, never dropping a single packet, creates a brittle architecture that fractures at the dimensions required for frontier AI models. Amazon Web Services engineered a specific hardware alternative to InfiniBand, known as the Elastic Fabric Adapter, or EFA. EFA operates on a custom transport protocol called Scalable Reliable Datagram. To prevent deadlocks, AWS engineers made a precise trade-off. They explicitly abandoned priority flow control and the requirement for ordered delivery. This topology illustrates the SRD protocol. Instead of routing sequential data, it fragments the payload and sprays packets out of order across intersecting paths. The destination software simply catches the chaotic packets and reassembles them into the correct sequence. This software-based reordering incurs a latency penalty, giving EFA a base latency of 5 to 10 microseconds. That baseline is noticeably slower than InfiniBand's sub-microsecond speeds for small message sizes. At Hyperscale, however, the critical metric is tail latency. Because the speed of the slowest packet dictates the speed of the entire cluster, consistency is far more valuable than raw baseline speed. This chart plots network throughput during extreme events. Because ESA eliminates head-of-line blocking, it maintains a stable, sustained line of throughput even when hardware fails or cables are pulled. Adopting this hardware requires a software adaptation. AI workloads must be rewritten, shifting from one-sided memory access to two-sided send and receive semantics. Engineers mask the higher base latency by designing algorithms with asynchronous communication patterns, increasing computational granularity so the GPUs keep calculating while waiting for data. Analytically, AWS chose system resilience and consistent tail latency over raw speed, accepting a slower baseline to guarantee that massive AI clusters never deadlock under load. The hyper-efficient packet routing at the microscale directly drives the massive power demands at the macroscale. This chart illustrates the Jevons paradox. Engineering optimizations reduced the energy required for a single AI prompt by a factor of 33, but total queries skyrocket exponentially. Efficiency gains are consumed by scale, driving total electricity demand higher. Deploying hyperscale AI requires mastering asynchronous data communication at the micro level and geographic load shifting at the macro level. The battle for industry supremacy has transitioned from software developers writing algorithms to infrastructure engineers solving applied physics. The frontier of artificial intelligence is bound entirely by the physical limits of power and packets.